Welcome everyone, and thanks for being here. We had a previous session for EV car. There was a demo there. It all looked very good, but there is one thing. I mean, things can go wrong in a wild scenarios, and to debug those scenarios, we need one very important thing to be in place, and that is we call it telemetry. So today I'll be talking about the auto instrumentation of Rust application using eBPF and OpenTelemetry. The idea is simple but powerful. Using the kernel intrinsics to instrument your user's space code without actually touching that code. So we'll be focusing mainly on distributed tracing, since that's the trickiest part if you want to do auto instrumentation. But keep in mind the same concepts we cover here will also apply to matrix and logs. So the picture is bigger than just the traces. Yeah, a bit about me. I'm Lalit Bhasin, as a principal engineer in Microsoft, one of the very early contributors to OpenTelemetry project. I started out in OpenTelemetry C++, uh, started the implementation, stabilizing it, and later moved to OpenTelemetry Rust, mainly because my company, Microsoft, they began leaning on Rust for system level work, and company could easily observe the gap in OpenTelemetry Rust implementation. So since then, I have been more focused on growing the Rust ecosystem for OpenTelemetry, and today I'm a maintainer for both OpenTelemetry C++ and OpenTelemetry Rust. Uh, as part of OpenTelemetry Rust, we also have been doing some early work on auto instrumentation. The goal today is to share the journey, what has worked, what have been the challenges, things which have not worked, we still don't have a solution for some of the things. So just wanted to share our learnings and hopefully inspire few Rust and eBPF developers to really start contributing in OpenTelemetry, specifically in the Rust space. Uh, First of all, I know it's a post-lunch, so probably people may be a bit droopy, so just wanted to have an audience poll. A quick check, please raise your hand if you have heard about OpenTelemetry. Thank you. Keep it raised. Keep it raised if you are using OpenTelemetry in your work or the personal work. Still keep it raised if you are really using OpenTelemetry Rust specifically. Wow, lots of hands. Thanks. You can just probably gives me a sense of the room, and thank you. And for those who are new, I think it will set up a good foundation if I just talk something about OpenTelemetry before really moving to auto instrumentation, and would be also a quick refresher for the people who have been already using OpenTelemetry Rust. So yeah. That's OpenTelemetry. This definition is coming straight from the official OpenTelemetry website. The key idea is that OpenTelemetry isn't a single product. It's a set of APIs, SDK, and tools. You use it to instrument your code, generate telemetry signals, collect them, enrich them, process them, filter them, and then export them to whatever backend you want to do with it. And when I say telemetry signals, I mean three big ones: metrics, logs, and traces. So at its core, OpenTelemetry is about giving developer a common standard of for observability. So you don't need to rely on a vendor-specific agents or fragmented tools. Okay, that's a bit more about OpenTelemetry. It's a CNCF project that unifies observability. It started in 2019 by merging two existing standards at that time, OpenTracing and OpenCensus, into a single standard. Today, it's backed by around 200 companies, thousands of contributors, and has grown into a second most active CNCF project after Kubernetes. The scale is what makes it the default choice for telemetry. Again, some architecture diagram, pulled it again from the OpenTelemetry official website. So as you can see in the diagram, telemetry can be something which can be generated by your own application, which could be a microservice having tons of different services. This telemetry could be generated using auto instrumentation, or could be using manual instrumentation. It can also be generated using the shared infrastructure which you would be using probably for your application, which could be a Kubernetes or some proxies, and could be also some external services like database or some shared APIs. So all these services, they generate a telemetry. All of them flows into the SDK, through the SDK into a OpenTelemetry collector, which normalize this data into OTLP format. It further does some processing, filtering, enriching, and eventually exports this to an write backend for matrix logs and traces. So I just mentioned a term called OTLP. It's an OpenTelemetry protocol. It's a vendor neutral wire format OpenTelemetry uses to reliably send the telemetry data to the backends. OTel collector can accept lots of different formats, but it will normalize all those formats into OTLP before doing further processing down the pipeline. Something about OpenTelemetry Rust. This is the current status of the OpenTelemetry Rust project. To briefly talk about, logging API and SDK are stable, matrix API and SDK are stable. The challenge currently is with the tracing implementation. The reason is that currently tracing is that we effectively have two different user-facing APIs. One is the Tokyo tracing crate, which has been widely adopted in the Rust ecosystem. The second one is the OpenTelemetry tracing API, which is OpenTelemetry specs compliant. So they don't, both of them does not perfectly align for distributed tracing. I mean, OpenTelemetry specification really talks about the distributed tracing, and this is how OpenTelemetry Rust user API is implemented. Then we also have, as I said, Tokyo tracing crate, widely adopted, somehow not fully suited for distributed tracing. So the community has been debating how to really interop with both these APIs, whether we should drop one of them or whether we should continue using both of them. So currently, the state is that both practical path is to keep both of them active and running and provide an improved interoperability across both of them. But as I said, tracing API is still not stable. The tracing implementation is still not stable. So please don't hold me on this. This decision can change over the course of time. This is what, I mean, as of now, being discussed upon. A quick about a core example on how we can do a manual instrumentation in OpenTelemetry Rust. So this on the left, yeah, on the left side code, we can see how to create spans directly in the code. So in this example, there is a parent span with a nested child span. Together, they form a single trace. On right side is about how to configure the application with the tracer provider, configure a tracer provider with a processor, with an exporter, and eventually export those spans to be recorded and sent out to an appropriate backend. So all looks good. Now imagine in a large code base, doing things this for every database call, every HTTP call, every service which you are maintaining. You will be spending most of the time doing the telemetry instrumentation along with your actual application business logic. So auto-instrumentation is where it takes the burden off the developers, and eventually that's what we are talking about, eBPF. Eventually that becomes one of the important talking point when we talk about auto-instrumentation for languages like C++ and Rust. Why auto-instrumentation? Auto-instrumentation solves three big problems. First is the legacy systems. It's not easy to really, legacy system may not be really instrumented to send the telemetry data. Suppose in the OpenTelemetry standard, or they may not be really instrumented at all. And it's not easy to add or modify the code to really start supporting tracing. large code base, manual instrumentation does not always scales well for large code base, especially when we always have a standard set of attributes which we want to export from the entire code base. Cross language distributed systems, uh, each runtime, each language has their own way to store the trace context, could be in a task local, as a thread local. It's a format which is really supported by the language implementation, and it's really difficult to propagate that trace context from one language to other language in case the application is a mixed language application. So that's other reason where auto instrumentation can really help out to set up the complete tracing pipeline. That's a typical auto instrumentation pattern which is used in managed languages like Java, C#, and Python. So in managed languages, it's relatively easy because the code runs inside a virtual machine. Agents can hook into the runtime, intercepts methods or libraries, and inject telemetry automatically. That's why auto instrumentation is so mature in these ecosystems. And if you go to the OpenTelemetry repo, GitHub org repo, you'll see specific dedicated repos for OpenTelemetry auto instrumentation for these languages. But this approach relies on a VM layer, and the native languages like Rust and C++ does not have that layer, which makes auto instrumentation a bit harder for these languages. And we'll talk about that. Yeah, so that's the challenge, as I just mentioned, for Rust and C++. In the Rust and C++, the code compiles straight to a native ELF binary. We are talking about the Linux, we're not talking about the Windows as of now, and I'll tell you why we're not talking about the Windows afterwards. So the code compiles straight to a native ELF binaries with no VM in between. You can still see system calls and functions in the binaries, but the release builds, they will often strip the symbol tables and remove the easy hooks which can be leveraged. There's no runtime layer to patch into, and specifically in the Rust and C++, there's no stable ABI, which means the function boundaries can change between the versions of the applications. Go somewhat sits in between managed languages and Rust and C++. It compiles to ELF binaries, but it also have a rich runtime with garbage collectors, scheduling, and go routines. So there is information in the binary which can be leveraged for auto instrumentation in case of Golang, but that's something which is missing for Rust and C++. And that's one of the reasons auto instrumentation for Golang is bit more advanced as compared to these Rust and C++. I mean, if you go to the OpenTelemetry repo again, you'll see lots of work already happening for auto instrumentation of Golang, and that's one of the reasons why it's there. We saw the challenge for auto instrumentation for native languages. What's the solution? eBPF is one of the solutions, and before really going forward how it can be leveraged, just wanted to give a brief about what exactly is eBPF. eBPF stands for Extended Berkeley Package Filter. You can think of it as a virtual machine inside a Linux kernel that runs sandbox programs safely. Safely is very important here. That means that once that sandbox program, we call it as a eBPF program, is loaded into the Linux kernel, it will never crash Linux kernel. It's unlike Linux kernel modules, or unlike doing patching into the Linux kernel where you have to really troubleshoot, iterate over. Sometimes the kernel may crash because of unbound memory access or any other reasons. This will never happen in case of eBPF programs. Once they get loaded, they are safe to run inside the Linux kernel. Something like running JavaScript over browser. Browser will ensure that JavaScript cannot make the operations which can really harm the system. It started, eBPF started very early. It's something which, specifically for the Linux. Again, that's the reason why we're not going to talk much about the Windows. There is a eBPF work happening in Windows, and I think hopefully by next year or something we should be able to talk more about eBPF on Windows. As of now, it's totally going to be on Linux. This eBPF is not a new technology. It started in 1990s. Basically, it was used for packet filtering. If somebody has ever used TCP dump, that was one of the first tool for packet capturing. That was one of the first tool which was using BPF technology. That time it was specifically for packet filtering, but over the course of time this has got evolved, and now it has been used for observability and also for security. If you have like LSM is being using eBPF. eBPF programs are event driven, so they won't run by itself. They wake up when something happens in the kernel, like a syscall or a network packet ingress or egress. So they will always run whenever there is some event happening in the kernel. The other important aspect is you can just compile the eBPF program once, and then you can run it in any Linux kernel, any version of Linux kernel. The only requirement is that the Linux kernel should be supporting eBPF. So it's a kind of CORE, compile one, run everywhere, and that's one of the advantage. You really don't need to build your eBPF program for all the kernels down the line. Just compile it once, create the bytecode, and that could be used across all the kernels. There are two main components of eBPF program. Of eBPF, one is a eBPF program. That's the actual code which runs inside the kernel. The other one is user space program. So eBPF can execute in the kernel, but we need some way to load that kernel program and also to be able to get the data from that eBPF program at the user space. So we have a user space program which the responsibility of that is to load the eBPF program to kernel and then also interact with that to get the data out of the kernel. I mentioned that eBPF program will not run by itself. It will only execute if there is some state change happening or some event happening at the kernel. So these are some of the events or the hooks where we can attach the eBPF program. There are user space hooks. I mean, I'm only covering the one which would be helpful for auto-instrumentation. There are lots of other event types. I'm not just as of now I'm ignoring them. So there are user space hooks. These are uprobes and ureturn probes. These capture user space functions. So these hooks can get executed whenever an application level function enters, and a ureturn probe will execute whenever the application level function exits. There are kernel hooks, kprobes, just like uprobes. These will execute whenever you enter a system call or exit a system call. We have trace points. These are the standard set of always available kernel hooks. The application can just attach to that hooks and start using them. We have network hooks. These are the two of them are XDP, the express data path, which basically attaches in the NIC driver at layer 2, at the lowest layer, so that it can basically, that's the earliest level of any packet filtering which we want to do it. And then there is a traffic control which can hook at layer 3 or 4. So it can parse the TCP IP packet, and it can do some decisions based on the actual protocol data at the layer 3 and 4. So now that we know what eBPF is, how can we leverage the eBPF technology specifically in the Rust? So there is already a Rust ecosystem for eBPF. One of them is Aya, and the other one is libbpf rs. Aya is pure Rust implementation. So as I mentioned, there are two components, eBPF program and user space program. Using Aya, you can write both these components in pure Rust. It does not rely on libbpf or BCC. libbpf and BCC are basically more native libraries through which we can write eBPF code. but IA does not rely on any of them. It does not require a kernel build or a kernel compile headers, not even a C toolchain. It just needs a Rust compiler with LLVM backend. It has experimental CORE support, so I mean it does provide a support, but I think it is still experimental. And then the other one is libbpf RS. It's a wrapper on top. It's a Rust wrapper on top of the libbpf C library. So in this case, we write the eBPF programs on standard C library and the user space program in Rust, and the compiler toolchain is CLang or Clang plus LLVM for eBPF programs, and we use a standard Rust compiler for user space program. CORE is supported by default. Most of the examples which I am going to talk here would be libbpf, using libbpf RS for no specific reasons. I know that there are IA maintainers and developers probably sitting somewhere in the audience. Please don't judge me. You guys are doing an awesome job. It's just that I have used libbpf RS and I just wanted to show that examples how we can leverage that for auto instrumentation. Okay, so this is the eBPF program, how we can leverage that for auto instrumenting and application. So the left hand side part of the code snippet, this is the entry probe, the uprobe, which we are adding. We have created an uprobe as an entry probe to add a bookmark. So what we do here is we capture a process ID, we capture the method ID, timestamp, and we create a context. If this is the root of our telemetry, we mint a new trace ID. If it's a child, we inherit a parent trace ID and record the parent span ID. A fresh span ID gets generated and it's stored in eBPF map. eBPF map is, as I mentioned, it's a way to send data from kernel space to user space. Also, it's basically a kind of caching mechanism inside the kernel space. The right one is the exit probe. This is when the function to be instrumented exits. At that time, we return to that bookmark which we already created when we entered the function. So we add the end timestamp, build a span with trace ID, span ID, and parent span ID. That span is put into a ring buffer, and that's a ring buffer from where the user space program will pick up that span to be eventually sent across to OpenTelemetry pipeline. And eventually, once that is done, we'll just clean up the state. So together, two probes have been added here. One is the entry probe and one is the exit probe, and they just don't capture the timing of this function. They will also capture the complete hierarchy, parent spans and child spans all stitched into a same trace. Okay, there are two problems here. One thing is, if you see, we are relying on to really maintain the trace information, we are relying on something called as thread group ID. Because at kernel level, we only work on thread group IDs. But in case of async functions, this may not will not work perfectly, because in async function, a given async function can hop across multiple threads. So if you really want to instrument a async function, you cannot really rely on thread group IDs at the kernel level. So okay, so now this is the user space program. We saw the kernel space program where we created a complete span hierarchy, created a span object, and we are able to put it in a ring buffer. The user space program at the left hand side, it loads the eBPF program. see there is something called as load somewhere called here. It loads this eBPF program from the disk. It's going to, it will load it into the kernel buffer. It's going to attach uprobes and ureturn probes to the functions which we really want to instrument. And then once it has configured loading the program and attaching the uprobes, it's going to start polling the ring buffer. The ring buffer is where the kernel space eBPF program is going to create this span and write it there. So user space program is continuously going to poll the ring buffer, and it will, for any new events, once the new events it's able to get a new event, it is going to use the OpenTelemetry to create the OpenTelemetry span out of that, and eventually export that OpenTelemetry span to the backend where we really want to do that. As I mentioned earlier, this code will not perfectly work for async scenarios, and this is what typical async code looks like. I mean, the eBPF only sees thread IDs, not the async tasks. Rust async runtime moves the task between threads, breaking the simple thread group ID based tracing, and context can be lost unless we find a way to track logical tasks like futures and wakers across the thread hops. So in this example, the async task may start at thread 1 till the await, till it encounters a await, and once it encounters a await, the task will be suspended. The await IO call would be executed, and it would be resumed probably in a different, could be in a different thread. So eventually a single async task may be executing in multiple threads, and that's the typical challenge which we have in eBPF programs. As at kernel level we really don't understand what exactly are the task level threads which are being used here. So a simple example, I think Tokyo would be a very good example to really showcase this state machine. And why I want to show this example is that we can leverage this state machine for our advantage for eBPF programs. So let's look the state machine. So initially with the task gets spawned. I mean, task is spawned at the time it is put in the task queue. Tokyo spawn API is called. Task is created, but it's not yet running. It's put into the scheduler queue. The task starts running. Tokyo poll is called, and the thread T1 is assigned, and task is running till await point is reached. When the await point is reached, the poll function exits with a pause state, and the thread goes, and the thread T1, the task is not longer assigned to thread T1, and all the threads are now available for any other task to really take it over. So the IO await function completes. Now again, the task is put back into the scheduler queue, from where some other thread will take it over, and that probably could be the thread different from the earlier thread. And now wake function is called to ensure whenever the IO await is completed, or Tokyo wait is called, and using that wait, it's put into the scheduler queue, and once it is in the scheduler queue, the different threads, say T3 in this case, will take it over. It will start running the poll again, and when the function exits, or the task exits, the poll will return, and the task is completed. So what I really wanted to tell here is that from the state machine of Tokyo, we know that what all functions Tokyo state machine is calling. There is a wake function, there is a poll function. If we can leverage that information to our benefit, to ensure to get the the swapping of the threads whenever it is happening, and if we can put the probes in those functions, we can get that information out of the, I mean the thread information from those tasks, and that we can leverage that inside our eBPF program. So that's something I just wanted to show it here. Attaching those probes to Tokyo spawn, Tokyo poll, when poll function start executing, whenever the poll function exits, Tokyo wake, whenever the wake is called, that means this is a time when this task is probably going to switch to some other thread. And when the Tokyo again poll is called, that means the task is going to resume. So we can use this is just a pseudocode here, but I just wanted to highlight that we can use this information to the benefit to ensure that we are able to identify that the current task is running at the eBPF program level, that the current task is running under which thread. So that was one of the challenge, how the async will work. There is another challenge, is distributed context propagation. So this diagram shows the distributed context propagation. So till now, whatever we have been seeing, that's the in-process context propagation, where we are calling one function from other function. But in case of distributed context propagation, the context has to go out of the network boundary, and auto-instrumentation becomes a big challenge here, because now you don't need to really maintain context information in a thread local or task local, but you really need to add that context information in the HTTP headers while the API calls are being done. So there is a W3C trace context specification which talks about the HTTP headers and specification, that how that HTTP header should look like. And this is one of the challenge, because using auto instrumentation, using the probes even at the network level, it's not really easy to add to append a new HTTP header specifically with the trace context information. So this is a challenge here. Like in this case, there is a client, the HTTP request is going all the way from client to front end to back end to database and comes back, and this complete is a one request flow, one trace, and we need to ensure that the same trace ID is flowing across all these components over the HTTP header, and so that at the backend side we are able to track the complete trace. And there are options how we can do that. So writing HTTP headers from eBPF. So this is a challenge which we have right now. There are ways of doing it. One of them is BPF probe write user. This is a BPF function which can be used to write into the user space memory, because right now what we have to do is the HTTP header is being created at the user space. We need to append another header in the HTTP request. It could have been created using request create or hyper create or any other create at the user space, but at the kernel level we really want to append another header in that, and that means we have to write something in the memory which was allocated at the user space. So there is a function BPF probe write user. Something was easy to leverage that to really add a new header to the HTTP, but the problem was this was something locked down in August 2021. eBPF does not really support that anymore. One of the reasons for locking it down was the security concerns. At the kernel level, any program should not be able to write something in the user memory. And another issue was that there was not a very clear use case scenario apart from auto instrumentation to use this function. And I think the trade-offs were more than actual use case in this case. So this is not really available anymore now. There is something called as BPF arena, which provides the unstructured flat memory shared across both user and kernel space. This is something which could have been used, but the problem is whenever the eBPF program is loaded, this memory gets zero initialized. What it means that if that the memory already has some HTTP headers allocated through the request create, as soon as we load this program, that memory will get zeroed out. So that can result at the user space program to really crash, or any undefined behavior can happen. Level 4 context propagation is something, another aspect which can be used. Uh, uh, that works fine, but the problem here is that it will not work with level 7 proxies like Nginx or any other proxy at level 7 running, because they proxies also have to be instrumented using the same way we are instrumenting our endpoints, and that is not always possible. Again, level 7 context propagation using HTTP is another solution, but the problem here is that encryption prevents reading and writing at level 7. Another option is library interposition or patching. This is more traditional way. This has been done till now. A non-eBPF way of doing is to hijack the calls to libcurl, libssl, libc, and basically trying to write to run your own code whenever say SSL write or SSL read is being done, and that code really, that intercepted code can really write into the header information. So we can use LD preload for that. Works great, and I think lots of times I have seen people using that. The only problem it becomes is that in case these libraries which have to be intercepted are statically compiled with your application, it's not that easy to really intercept them, and needs more patching and becomes a bit messy. So yeah, so that's one of the challenge. No right way of doing this for at least the context propagation across the network. Some of these ways may work, but there is no one all good solution as of now for context propagation in the distributed scenarios. Probably I'll just skip it. I think this is some talks about the same context propagation. Yeah, general requirements, limitations of eBPF uprobes. One of the basic requirement is that the target function which we want to auto instrument should not be inlined, should not be a macro. In those cases, these would be compiled out, and you really won't see at the kernel level, and they cannot be instrumented. Functions, symbol tables should be there. That's the must requirement. Without symbol tables, we won't be able to instrument these functions. There is possibility of doing offset based attachment in general, but that's a fragile and mostly not recommended. So yeah, these are some of the basic requirements if we want to leverage the eBPF for auto instrumentation. State of eBPF based instrumentation in OpenTelemetry. As I mentioned earlier, that Golang is one of more mature in terms of auto instrumentation. We already have Go auto instrumentation work happening in OpenTelemetry. It uses eBPF to trace the Go application without any code changes. Works good. Lots of go-to work is happening in this for a long time. Bela already has a multi-language eBPF agent. There was a proposal to donate by Grafana Labs. So Bela is one of their multi-language eBPF agent, and the plan was to really donate it to Grafana, to OpenTelemetry. It's already done. I think it's already part of the OpenTelemetry project. It's more language agnostic, protocol level, still very limited when we talk about Rust and C++. It does not really support at that level. There is a eBPF SIG special interest group which talks more about collecting the kernel level telemetry, more in terms of profiling the kernel level. So there is some work happening at eBPF in OpenTelemetry. I'll say not much in Rust or more native Rust and C++. So that's something I think we are probably lagging, and we'll really look forward to make it more mature. And I had a demo, but I think probably I'll be sharing it, the setup, over the Discord. I think it was slightly complicated setup to really come up here. If there is an interest, probably I can share it across the Discord, so people can really try to see how it runs. Thank you. I'm reachable over the Discord or even the Discord channel for this session, so please connect me there. And